inviting me to give this talk. This is on central banks, inequality, and new technologies. The subtitle is Blueprints Using Distributed Ledgers, Programmable Contracts, and Cryptography. So let me begin by reversing the title a bit and starting with inequality. President Xi Jinping has emphasized inequality and common prosperity, and what is meant by this is sharing the opportunity to be wealthy. It is a long-term, arduous, and complicated task because, among other things, it has to deal with the relationship between efficiency and fairness. And indeed, different regions and groups of people may enjoy different levels of prosperity over various timelines. So then the next segment has to do with the role of central banks, and this is from the BIS. Agustin Carstens and Luis Pereira have emphasized in separate talks the role of monetary policy and central banks. The poor are disadvantaged and disproportionately injured if central banks don't follow the traditional mandates of stable prices and sustainable economic activity. Monetary policy transmission channels are impacted by inequality, which is a key part of heterogeneous agent models. And in addition to the standard mandates, many central banks include increased financial access, provision of a competitive and efficient payment system, and fostering financial development as goals. So finally, digital technologies can both promote greater equity and efficiency and boost the transmission of monetary stimulus. So all of these aspects are interrelated. Then the third word of the title, the new technologies, I'm going to be emphasizing in this discussion the programmable contracts, cryptography, and distributed ledgers as related to these goals and inequality and the role of central banks. And the order of the presentation will be inequality, then financial access, then competition, and then monetary policy. So I want to begin by an example because I have learned that it's important to be very specific and concrete. And if one speaks in the abstract, then the message gets lost a little bit. So although I think this generalizes, it is illustrative. Thailand, a case study where you are seeing here maps of income and how it is spatially diverse, however, increasing over time with the concentration around Bangkok on the eastern seaboard and then the corridors running north and south. However, on the opposite side of the screen, you can see wealth, and wealth inequality is being measured here. As you can see, there has been little change over time. Stubbornly persistent. I am mentioning Thailand because I have the advantage of having a lot of data. I have done research and data collection there for over 20 years, so I have data from rural, urban areas as well as annual and monthly data. You can see highlighted the diverse provinces all over the map of the country, and in detail, one of the provinces, Sisaket, which is out of the northeast, you may remember is one of the poorer areas. You can focus on the little dots, which are villages, the road network, and then the areas where I've done all these various surveys. And if you look really hard, you can spot the icons for Bank for Agriculture and less prevalent, the private commercial bank branch location. So I'm making the point on this slide that we have the advantage of data for analysis, but also that financial access is limited. Now, what you can't see going into a village is that the government put a village-level $1 million fund in each of them midway through actually earlier on in my data collection, and you're not seeing the informal money markets of the village. And I'll come back to that. So let's look for what works and what doesn't work on the ground, as it were. I'm showing you here a selected mechanism design problem, a social contract solution of this problem. And this is for households in these villages that typically run small and medium enterprise. So in broad terms, what we're doing here is maximizing the ex-ante expected utility of the households running these SMEs in a village, subject to the state variable, which is initial wealth, and then the disposition of wealth. So they have initial state from production and previously acquired capital, and that can be used in consumption or capital going into the next period. A key variable here in the utility function is not just the output and wealth of the individual, less the amount of investment for the next period, but also the transfers talent that can be positive or negative. So the basic idea here is that when a household is fortunate to have a high return, they will potentially transfer and share that return with other households in the village. And likewise, if they're low, they could receive an indemnity, although this arrangement is not normalized as an insurance contract. So what we should see, if markets work perfectly well, is that the expected return on these technologies that they're running, farms, businesses, and so on, should be higher, or needs to be higher, to compensate for risk. But the risk is at the village level because they've already pooled their resources, according to this theory, so that if the return of an individual is highly correlated with the village, it's not doing the rest of the village much good. Something much more valuable that doesn't require as high as expected return would be a household doing something that few other in the village are doing, so that its return is not co-varying with the village average. I've also put on this slide what happens in autarky when individuals are on their own, in which case they face more risk because they can't pool it, and that in fact can deter them from investing in productive technologies. These are villages, but please don't think of them as closed economies. They're open economies with at least borrowing and lending, if not other flows going on across the villages. So using the data that I have, we can decompose the shocks that are experienced by these households running businesses into idiosyncratic shocks, which hit them alone and no other, versus aggregate shocks, which hits them all jointly. Key finding is that the idiosyncratic risk is huge, much bigger than the aggregate risk at the village level. But on the other hand, when you look at the risk premium, as per the previous slide, the difference between the expected return and the sure return, that premium is higher for the aggregate risk than for the idiosyncratic risk. And how can that be happening? The answer is they are pooling, actually, quite explicitly, giving gifts to one another, and borrowing and lending with each other. So when the shock is high, their consumption does go up a little bit, which contradicts the pure theory. On the other hand, 10 times more of that is given away in terms of lending and gifts. Unfortunately, this mechanism isn't working for everyone. If a household doesn't have kin in the village, they're in trouble. If they do have kin, then they use these gifts to fund investment, not just smooth consumption, investing for the future. In fact, from the data, we can see that there's a regime shift when the village fund that I mentioned earlier comes in from simple borrowing and lending to costly state verification, but only if they have kin in the village for the relatively poor. They could have be highly productive individuals with high TFT. The village fund did not successfully allocate credit. It was more randomly distributed. But if a household had a link through kinship to someone who got the money, then indeed they invest more and their profits go up. So there's a lot of risk sharing and giving and so on within these village networks. But the downside, these networks are not always good. If you're not in one, you're in trouble. Indeed, a household experiencing high expenditure shocks without getting gifts will transmit that adverse shock to others via hiring less people and not buying in gifts from other households in the village. So let's think about how to improve the situation for these households without kin in a village by giving them a solution to a mechanism design problem. So the idea here is to illustrate via this simple example that when the shocks are low and they have adverse balance sheet shocks, they're urgent to consume, or they could be doing just fine and be rather patient. So agent A here experiences a shock first. In the first period, then agent B experiences a shock in the second period, and this is the solution to maximizing the weighted sum of utilities. There's a lot of information on this slide. The short way to view it is that if the household is urgent, they're going to get more consumption than when they're patient. But household B in the second period is in an odd position because it is going second. And indeed, it's very important to conceal from household B what happened and what was said by household A in the first period. There is an outcome here, 1.75, 8.25, which is occurring with positive probability, regardless of whether A is urgent or patient. And that scrambling of the allocation keeps agent B in a relatively uninformed position. And that is crucial for engineering the insurance indemnity to agent B when agent B is urgent. This is the solution to the mechanism design problem. In economists, we act as if there were a planner solving this problem, but in practice, in reality, there may not be a trusted third party to run the mechanism. But that's okay because we can code it all up. So here, a pseudo-agent C in the protocol can split information. This C code would know the order in which agent A had sent the low and high shock, but when the mechanism is played out over time, the actual message M is concealed to the code. So the code remains ignorant, even though it has crucial pieces of information that agent B does not have. And so using homomorphic operations on the encrypted space, the mechanism can successfully randomize even though there is no person running it. And this is ongoing work with Nicholas Sang and myself. This is using both fully homomorphic encryption and multi-party computation. Let's come back to the cross-village problem. Each village has an aggregate shock, but shocks vary across the villages. And there's no infrastructure, unlike the $1 million fund in Thailand to build on. But we could propose a mechanism in which individuals in a village are reporting, as on the previous slide, their incomes concealed via encryption, but one can add up, essentially, those encrypted messages via multi-party computation and get the aggregate income. So in this case, if the aggregate income shock at the village level is low, the village would get an indemnity from other villages that had more favorable outcomes. And one could even, in principle, keep the aggregate shocks private through the encryption. So this is known as secret sharing. And I'm sure the audience here is very aware of the meaning of encrypting your own messages, but then taking out the random noise at the end, leaving the aggregate for everyone potentially to see. There is a larger point here, which is that we're doing the solution, the combination of off-chain and on-chain ingredients. So off-chain, there's this smart contract that maximizes the expected utility of the participants. In this case, in this picture, agents A and B experiencing these balance sheet shocks, which they announce, but it encrypted, going to code C as a smart contract. And the contract then dictates the transfers on the ledgers, so that's where the distributed ledgers would come in, giving a new state on the balance sheet. So this idea of doing things off and on-chain is certainly not new. David Mazieres with SpeedX, the Lightning Network, which is cross-chain, so-called Layer 2 solutions for Ethereum, and interplanetary filing systems are all using this off-chain device. So I actually in the talk have been saying deliberately programmed contracts rather than smart contracts, because people will confuse smart contracts with an insistence that it be run on Ethereum, whereas here we are doing things programming but off-chain. So what does it take to implement something like this? We need something trusted on the ledgers, and central bank digital currency is one such object. Or it could be synthetic coins or fully backed stable coins, but something that's effectively tied to fiat. And then you do the programming as in the contracts with the outcomes in the CBDC. Second ingredient, we need partners. We need to reach down to Main Street. We need to get a partner in a given country that is aware of all these tools through DeFi, but willing to reach out to SMEs and households. And finally, when you get to the village level, you need what is called the last mile. Villagers may need help in understanding the technology, the apps, in terms of cash management, life cycle planning, and financial training. And again, in the context of Thailand, we have created these local tools. So let me come back to inequality. So what happens if you do implement some of these technologies, not only for a given village as an experiment, but scaled up? So this work with Engineer Da Silva is about risk-taking over the life cycle. Again, to tie back to the data, we are matching in the model the aggregate and idiosyncratic risk premia that I mentioned earlier, the degree of inequality, and the life cycle profiles of consumption and risk-taking over the life cycle using that 20-year monthly panel. So then we can envision in the model counterfactual reforms associated with digital technology and programmable contracts. One reform would relax the risk constraint by allowing better pooling among the non-kin strangers, which would lead to a reduction in the idiosyncratic risk premium. And actually in the model, that leads to an investment boom, although subsequent generations and entrepreneurs would not benefit so much, or maybe even be injured due to economy-wide crisis. The second reform, but a different one, would allow households with some member running business to capitalize the labor income of other members. So this is literally human capital put on the distributed ledger as an asset, which would allow more borrowing, and this too impacts the life cycle, physical investment, and equality dynamics of the entire economy, but in a different way, and the model is important for allowing us to trace out these differential impacts. So let's come to the use of mechanism design and how to think about competition. So Zhu Xiaoshuang has written on the need to reflect on during money, that in the digital economy, he thinks that only specific areas are actually areas with economies of scale and winner take all, but too many people act that way, squandering resources. I totally agree with this line of thought. First of all, there is a benefit to competition with providers competing with each other to give the best contracts and so on. So ex-ante competition is good, but ex-post competition can actually be a problem because it undercuts the beneficial ex-ante incentives, and perhaps that is a version of why some concentration of power should remain immune to threatening competitors if they're doing this adverse thing. There's another literature on innovation in financial markets, which requires different providers to coordinate with one another. That runs against traditional regulation, which insists on putting products and services into boxes and trying to make sure that a given provider is not doing multiple things. Here we get the opposite in terms of the needed improvement to conceptual improvement to regulation. Economies of scale, as Zhu Xiaoshuang said, is not necessarily so prevalent, even though you could have increasing returns if the marginal costs eventually, though declining, stay higher than the marginal benefit. You truncate the size of the entity, and that can allow competition across entities. More data helps, yes, but there are diminishing returns to having more and more data, inevitably through statistical considerations. And network effects, so-called DNA of big tech. Again, there is a solution to this, but it is better market design. So the externalities associated with multi-sided markets can be internalized by creating the right market structure in which participants pay for the right to join platforms depending on the number and type of participants on the platform. And again, if there's increasing marginal costs, one can get competitive outcomes despite network effects. Mechanism design and data brings us right back to encryption and program contracts. Again, there's work on decentralized identity, which makes the point that with judicious use of public and private keys, one can disassemble transactions and data and mitigate market power. Also, ZK Ledger is a way for government authorities to see certain aggregates, but not necessarily all the individual transaction partners. And design of data infrastructure, for sure, needs to be programmed. Programmed information dissemination can be a very good thing because it prevents an unraveling problem with adverse selection. So AI and big data can be fine if it's all automated and pre-programmed. Likewise, there needs to be control over information acquired by settlement platforms. They should not have a right to sell that data. They could actually make the situation as bad as possible due to exploiting the value of data when they exacerbate the adverse selection problem. And atomic swaps, at least without further cryptography, which are so advertised to be beneficial, can actually be adverse because information is leaked if you don't have the cryptography. So let me conclude with a slide on monetary policy, which is sort of the natural domain of central bank digital currency. The view here is that if you have the underlying micro data among firms measured on distributed ledgers or consolidated databases, you can use that to determine optimized monetary policy, not just the interest rate on the digital currency, but also injections to participants, the poor that suffer from limited access, not just with COVID, but on a regular basis, and likewise at a wholesale level. Liquidity injections can make sense if they're directed toward actors who remain in the market when the markets are thin and volatile. So there is a literature on monetary economics that talks about money as memory, money as a record-keeping device, and here monetary theory and the new technology become coincident. And the idea is to use the ledgers and encryption in such a way as to allow the monetary authority to vary injections into the economy depending on the underlying state of the economy, which they would now know better due to all the data. And this can deal with incomplete markets and the poor in an optimized way, not as a special targeting way, but as an intrinsic part of monetary policy. So I have taken you through remarks on inequality, shared prosperity, and central banks. Thailand is a selected country showing inequality in financial access, with gaps on the ground that get remedied with fully homomorphic encryption and multi-party computation, both aggregate and idiosyncratic shocks. Those innovations and the impact on the overall economy and on inequality can be done through model simulations. And then I continue to use contracts to think about approaches to competition, to big tech, to data infrastructure, and finally to programmable monetary policy using microdata. So thank you very much for inviting me to give this talk. Although it is pre-recorded, I'm eager to follow up, so don't hesitate to get in touch with me in some way, on my email perhaps.